Okay, today I'm going to talk about a very basic of things you need to know in real analysis or advanced calculus, such as the theorems and definitions, which I have uploaded in other videos. But this is going to be the very basics of what's the definition, what is a set, and as you know, in any mathematics, so if you're watching this, you definitely have done a lot of math classes. We want to know the basics, and we take for granted that you do not need to know the basics, therefore you're an expert because you know what's an even number. 2 is even, 8 is even, 9 is odd. But if you have made it this far, you need to know what even means. What's the definition of even? What is the definition of set? So we're going to take a look at very, very basic, simple. It may sound simple, it may sound basics, but you may think like, I don't need this. But guess what? In writing a proof, if you do not really master this, you're not going to do well in your proof. So let's start with, again, there will be definitions and theorems. And I'm going to start with a very, very, very basic called the set. What is a set? A set is, if you recall from ages ago, suppose we start with capital letters, right? So I'm going to call set A, and I put an equal sign, and it's going to start with curly braces, and I'm going to put some stuff in it, which means elements in it, which means numbers or, pictures or anything. But here, real analysis are dealing with numbers, so I'm going to write number 1 and 2 and 3. So in this case, if I close with a curly bracket, I only have 3 elements, A, 1, 2, and 3. So I can have more than one set, and I'm so used to only studying sets with capital letters A through Z. Okay, so what does it mean? Suppose I have, so let's say I have, I'm starting by saying I have 2 sets. And I'm going to call my sets, shall I call A or B? Let's call X and Y. So suppose we have sets X and Y. So we will say that the sets X, so you have curly braces with elements in it, is equal, so we're talking one set X is equal to set Y. So the set, so I won't say sets, the set X is equal to set Y, which can be written as X equals Y, aka X equals Y, if and only if. So in math terminology, IFF is if and only if both the sets, so both X and Y, contains exactly the same elements. So this is very basic, but I still want to stress it. So if you are just getting introduced to real analysis, I know a lot of friends and students who have no clue how to proceed with real analysis because they think this is not important. But after studying real analysis, I know you have to drill this into your own heads, right? Okay, so that's one definition. Then another definition where we don't even have to tell you, you should probably know it by heart, is what is the definition of empty set? Well, it gives it away, right? Empty set. So suppose you have empty set A. All it means is you have set A equals, you have the set notation, nothing in it, null, nada, nothing, right? And in mathematical terminology, I used to teach this in algebra classes. The notation is null set, empty set, with 0 with a line cross it. So make sure you remember that. It may find, I think this is not important, but it is important. Now let's get to serious stuff, which you're going to use for your proofs. So suppose you have 2 sets. So suppose we have, again, I'm going to use X and Y here. I may switch to A, B, C if I want to. So suppose I have sets A, and I want those elements in set A to be equals to set B. which is already defined above right there, right? They're equal. So if I say every element in A equals to every element in B, then I have two ways of writing this. So what does this mean? So if I have every element is also an element of B, I can say that A is a subset of B that's denoted as A subset equals B. Okay, so one is, this is exactly equal right here, A equals B. This one is a subset. Every element in A is also in B, in this case, denoted by A subset B. But suppose you have every element in A, but not everything is in B. So here we will say that A is subset of B as well. Oh, now what is what, right? But the notation is going to be A subset of B, but the key word here is not just subset, but proper subset. So an example would be, you have A in this case, so instead of XY I'm using AB, and you have B in this case. A contains in B, but not everything in B is going to be in A. So this will be A subset B. So if I have everything in A, also everything in B, they overlap with each other, this will be A subset of B. So if I just use the word subset, it's everything in A is everything is in B. If it's proper, not everything is there. So in order to prove any set A equals B, you must prove, you have to prove that, so I will say have to prove that A is subset of B and B is subset of A. So this is how we are able to prove equality of two sets. Okay, let's take a look at other simple theorems that we want to use in this. So we have taken a look at definitions. Now let's see if I can find, I have written down several theorems here. So let's take a look at theorem now. So suppose I have three sets. So say, or suppose I have sets X, Y, and Z. So suppose these are three sets. Then these properties are all needed in order for us to prove stuff. So in this case, this is a theorem, so you'll have to prove it and you'll be able to prove it. So we're going to talk about intersection and union in this case. Oh, wait, in order for me to do that, again, we need the definition of intersection. So intersection means, or let's do, instead of definition, let's just do notation of intersection. So let's note that intersection, you should know intersection by now, right? Is denoted by upside down U. That's what I would tell my students. Or union, we'll take a look at the definition later if we have time. It's going to be, looks like U. Okay, so this is a side note. Got a little sidetracked right here, but there you go. So now suppose we have three sets, X, Y, and Z. Then we can say that set X intersection with set X is going to give me X itself. The same thing will apply for union. So let's do for intersection first. This is called, I believe, idempotent. Yes, it's idempotent. Suppose you have set X, but now you want to intersect with another set. That means you need to have common elements in X and Y. That's a definition, right? This is going to be Y intersect X. This is, in math, is commutative property, right? Suppose you have set X and then you're going to intersect it with, but you put parenthesis, set Y union with Z. This is actually so let's do union. This is going to be set X intersect Y, then close parenthesis, set X intersect Z. What is this called? Distributive or De Morgan law, right? So these are some of the very, very basic properties, and you know there are many basic properties that we can look at. Alright, so since I promised you, or I told you I'm going to talk about definitions, let's quickly review what is the definition of, let's say I give you set X and set Y, because I'm going to talk about intersections and union. I just need be two sets. Then I will say that a union is denoted by U, not a U, but just looks like U. It will be, the set is defined like this: X union Y can be written in a set notation for all X such that, so when you put a line here, such that X is in X or X is in Y. So X can be the set of all elements belong to either X or B. So that's the meaning of union. What about intersection? So intersection is denoted by this symbol right here, and I can write it as X intersect with Y, and the definition can be written in a set notation where for all X we say that X is in X, so little x are the elements, capital X is the set, and X is also in Y, so they overlap, right? That's why you call it intersection. So the set of all elements that belong to both X and Y. And the next very important set terminology you need to know is called the complement. So the complement of, let's say, Y in X. So it's in X, but it's not in Y. So there are many notations people would write. I am so used to say X intersect Y complement, or X minus Y, as long as you know it's a set, it's not a regular math operation. Or some would say X backslash Y. So it's a set of all elements in X but not in Y. So the way we would write this notation is, so no matter what notation you pick, in set is going to be for all X such that X is in X, and so that's why I like using the first terminology right here, or first notation right here, and X is not in B, and is also very similar to not. So X is in X, but X is not in this case I use a not the Y. And so that answers the basic knowledge of set that you need to know. Memorize it, know it, and then you're done, and you can move forward with the rest of the chapters that we have. Thank you and keep watching.